Baroda, and many more. So IIW India carries out various activities and programs, and it is the now recognized as one of the premier institutes in the nation, which is having more than 4,500 plus membership strength all across the nation. IIW India is a member society to the International Institute of Welding, along with other 57 countries. So IIW India is our face to the global welding community associated with the International Institute of Welding. What are our major objectives? These are one of our major objectives. Say, for example, we are assisting the human research development in welding in India, activities and programs, and it technology diffusion to the industry and to the individual. We also help people in regards to research and development in welding. We also focus on promoting the health and safety aspects in welding, and we try to give knowledge to the industry about it. We also have establishing international standards of quality for the Indian fabrication industry. Next slide. So, what are the various activities that is adding value to an individual and to an organization? So, yeah, we do conduct technical meetings, we do conduct workshops, and nowadays webinars. So, this is our World Tech Talk series, which we are doing every Saturday. You all are getting benefit of it. Organizing various seminars, conferences, and exhibitions on welding and alloy technologies at various branch levels and also at the national levels. And even we do participate in the international level of such events organized by International Institute of Welding. Besides that, we also have a Indian Welding Journal, which is getting published quarterly in collaboration with AWS, American Welding Society, and we do have a monthly newsletter also, which is available on our website. So this is the website, you can just go and look out for yourself. So if you are a member, you can avail much more benefits. Next slide. Some more activities related to career development of an individual in regards to welding industry. We do give help people to get qualified for these certifications or qualifications like international welding engineer, international welding technologist, and many more. With regards to skill development, we are connected with, for example, automotive sector skill council and many other skill council bodies to develop the welder skill, particularly in the nation. So we are heavily involved in such kind of activities. Next slide. So as we have spoken about technology diffusion, how we are doing it? We are doing it by means of publishing journals, conducting technical programs, and skill development programs. Besides that, AMIW examinations are also being conducted, and national level welder and best welder and best welding engineer competitions are also organized by IIW India. When I say welder competition, it covers both male and female. We do carry out training courses, which is meant for training the trainers, and we also help industry in acquiring ISO 3834 kind of certification schemes. Next slide. Yeah, coming to the benefits of becoming an IIW member, you can take advantage of various courses and examinations that will help you in your personal career in welding industry. You can have a platform to disseminate your knowledge in welding, to add value to yourself and to others also to get benefit, useful networking with fellow national and international experts, free access to quarterly published Indian Welding Journal. So the journals which I spoke about, you can have access to those journals, and you can avail concessional charges whenever you are attending any welding seminar or a technical event organized by IIW India. Next slide. We have different types of memberships for an individual, which you can see it on your slide. You can be a member, you can be an associate member, or even from the college you can have a student membership also. So these are the criteria, and we'll not discuss now in details of this. You can reach out to us, and we can discuss about your membership. Next slide. So this is the membership fees for individual with regards to various categories. So this is just for your reference, and you can come back to us if you are interested in becoming an IIW member. Next slide. Besides an individual member, your organization can also get benefits of being an ICM, that is nothing but industrial corporate member. There are three categories of an industry or an organization that can be a ICM: class 1, class 2, class 3, and these are the description of the fees for ICM. Yeah, next slide. Yeah, so that's a quick introduction to IIW India and Mumbai branch. Details are there on your slide. You can reach out to us for any of your welding related queries, and if you're interested in becoming an IIW member, please reach out to us. Thanks, thank you all. Over to you, Nimesh bhai.
Thanks. Thank you, Abhishek, for the quick and lovely intro to the IIW and its activities. Can I now request Dr. Krishnan to introduce Chris, who in turn would be introducing our guests today. Dr. Krishnan, you're on mute, please unmute yourself. Krishnan, you're on mute.
Good evening all, and welcome you all to the next Tech Talk, which is it's in fact eagerly awaited one on aluminium. So we have an eminent panel today joined by Mr. Jan, who is going to be the speaker for the day, Mr. Chris Weissman from the Welding Institute UK, and we also have Dr. Prakash, who is actually an associate professor in one of the leading college in UK. So I welcome all the panel members and all the regarding Mr. Chris Weissman. He's a material scientist and has spent almost 30 years in R&D career with a global aluminium producer. So he has a lot of rich experience handling aluminium, and he has indeed contributed a lot towards corrosion, thermomechanical forming, novel test methods, and various process optimization, joining and surface treatment. And Chris joined the Welding Institute UK in 2007 and is a corporate membership manager for both aerospace and equipment, consumables and material sectors. So Chris is not new for us. He has been associated with IIW in past as well for the various previous lectures. And today we have one more guest in the panel, who is Dr. Prakash Srirangam. He is currently working as an associate professor at WMG, the University of Warwick, Coventry, UK. His research interests are in metal processing, dissimilar metal joining, and now I invite Chris Weissman to introduce our speaker for the day. That's Mr. Jan. Over to you, Chris.
Okay, thank you, Krishnan. And good evening, everybody in Mumbai. I hope everybody's safe and well over there. And thanks very much for inviting us again to join you in one of your Saturday technical meetings. I think today's topic is very interesting, particularly for myself. It reminds me of when I was younger and had a technical role in that industry. So one of the things I remember very vividly about 15, 20 more years ago even, we were trying to sell aluminium to the automotive industry. And Jaguar, who are not far from where I live, actually asked my company to show it how to put aluminium together. And we entered into a whole raft of projects ranging from surface treatments to spot welding through adhesives, that kind of thing. And that's when I particularly became aware, because I'm not a welder, how difficult this material can be. So I'm hoping today Jan will throw a bit of light on some of the practical aspects and the characteristics of aluminium that make it a very special, difficult, but a well worth material. And particularly going forward as we're looking to lightweight in many different industries. So Jan and I have quite a lot in common. Not least, I think he's almost as old as I am. We both live in the West Midlands, which means we both can just about understand Birmingham accents. But there the similarity ends, and I think you can see that straight away. It's around our heads. And I do remember when I last saw Jan in person, he actually recognized me in a crowded room and called out my name from behind, and he purely recognized me from my lack of hair. So it's quite an interesting feature. Jan is actually the technical manager for something called the Aluminium Federation. And this is an organization which TWI is very proud to collaborate with from time to time, particularly technically, but also commercially and sector-wise. So it's known as ALFED for short, and it's actually headquartered not far from where I live in a place called Halesowen, which is in the Midlands of the UK. And ALFED basically represents and creates opportunities for companies and individuals who may work with, process, or trade in aluminium. And ALFED is very UK-centric, but it also has a global reach and remit. Jan himself is a successful metallurgist. In fact, like many of us, he started his career or was trained in steel and ferrous materials. But I think we both quickly realized there was a future for non-ferrous. He's basically been delivering technology for many years into industry, ranging from manufacturing right up to large capital projects. And during that time, he's obviously developed extensive networks in business, and importantly, particularly in the UK these days, with academia. So there is a whole network in the UK which supports each other, ranging from government to academia and to business. And that's where ALFED and Jan play a vital interfacing role. So today, his role is as an advocate for the aluminium sector. And he lends his energy and expertise to research, innovation, and best practice to help make members of ALFED more competitive and skillful in delivering aluminium into industry. So without further ado, it's my pleasure to introduce you directly to Jan. And Jan, we're looking forward to your talk. Thank you.
Okay. Good evening, everyone. Hopefully I can start my presentation if it works. I hope everyone can see that.
Yes.
Good. That's a good start, because it's normally a disaster at this point. That's me. You're always welcome to email me with questions. You can ring me if you want, and I'm on LinkedIn. So please make contact with me. Please get in touch with us. I mean, we support the Welding Institute in the UK. There are my contact details. Please feel free to get in touch with me. All my life, I've worked in steel. In fact, before I moved to the Aluminium Federation, I used to work for Caparo, and I spent a lot of time in India. I spent a lot of time in India working on high-frequency welding the tubes and working on flash and butt resistance welding of steel. I'm not going to talk about that today. I'm going to talk purely about aluminium, and what I'm going to try and do is draw out how easy it is to weld, because quite honestly, there's a lot of misnomers about it. Aluminium's a light metal. It's actually got 34% the weight of steel. And typically the big advantage is it gives a 40 to 50% weight saving when you're talking stiffness. So if you're designing beams, if you're designing cars, you get a 40 to 50% weight saving over steel. And these days there are aluminium alloys. If you're talking body in white and architectural, there are aluminium alloys that match the tensile yield strengths of those. I'm not picking up on corrosion resistance today, but aluminium has incredible corrosion resistance. So if you couple that with its weight saving, it's beginning to dominate European automotive. Its growth is phenomenal. At the beginning of 1900, we were talking 1,000 tons of aluminium. In 2000, the world produced 20 million tons of primary aluminium. Before COVID, we were 60 million tons. No one really knows what's going on this year, but the demand will be 95 million tons by 2021, with recycling starting to dominate production as well. Aluminium is a light metal, so we should never talk in weight of aluminium, we should talk in volume. So in 2021, we're going to have 1/3 of a billion tons of equivalent aluminium to steel. Steel production is about 1 billion tons. If you talk in terms of the equivalent volume of aluminium, it'll grow to about 1/3 of a billion of tons. The predictions are that by 2030, we will be approaching 500 million equivalent tons. So let's pick out the problems of welding aluminium. The very, very first problem that you're going to encounter, yes, we can match the strength, but it's got a very low Young's modulus. It's very elastic, very low melting point. When you heat it up, it rapidly loses tensile and yield strength, which is actually a big benefit. The thing that frightens everyone is its ability to form a tenacious oxide, which is actually a benefit in many things. It's got high electrical conductivity, high thermal conductivity. It's got low resistivity, and it's got high thermal expansion. From the welding point of view, fearful properties, but they are absolutely easily understood and easily controlled. Because aluminium is a young metal, it's been developed by metallurgists, and incrementally, the series have been developed. Very, very briefly, the 1000 series are pure aluminium. The 2000 series are based on copper, an age-hardenable aluminium. 3000 is an improved manganese version for high resistance. 4000 is actually specifically designed originally as a filler for welding. 5000 dominates automotive, non-heat treatable. Then we come into the high tensile, the 6000 and the 7000 series, which dominate aerospace. In terms of weldability, the 1000 and the 4000 series have incredible weldability, as good as any steel once you understand them. The 3000 and the 5000 series have got very good weldability. The 6000 has good weldability once you understand how to weld it. And then you run into the problems. The problems of the 2000 and the 7000 series of aluminiums. These have got very limited or very poor weldability. We'll pick on those out. And then there's a mismatch series of 8000 series, which is looking at medical, nuclear, bearings, everything else, very variable welding in that area. So let me pick out the first property. Aluminium's actually got a low Young's modulus. It's about 1/3 that of steel. So although we can match the yield strength and the tensile strength of a lot of alloys, it is far more elastic. And that elasticity means that when you're doing things like forge welds, you've got to do a lot more effort. So in a typical forge weld where you want to upset, you would need to put in about 3 times more upset deformation to achieve a forge weld in aluminium because of its low Young's modulus, because of its high elasticity. It's very, very springy. That springiness is great when you're designing suspension components or crash cans or things like that, but it's a problem. So when you forge welding it, when you're upsetting it, in essence, you've got to do 3 times more plastic deformation to achieve over steel. If you don't, particularly in a forge weld, you end up with a wide weld center line, which is effectively a fusion rather than a forge weld with poor strength. So the very, very first, so easily overcome problem of aluminium, low Young's modulus. Pick out an important property. Aluminium's got low melting points. Pure aluminium melts at 660 degrees C. If you look at the higher aluminium alloys, they have low melting points down to about eutectic temperatures down to 450, 470 degrees C. So it's a very low melting point metal. At 450, 500, you're below red heat. So very low melting temperatures. That has implications in that we don't form scales, we don't need complex tooling, we're not got thermal losses, we've not got radiation losses. So it's a plus and a minus. One thing you need to understand when you're talking about aluminium is exactly what we mean. And when we warm aluminium from room temperature, we have to put a lot of heat in. And effectively, it's specific heat. And that's the energy required to raise the temperature of a metal or of aluminium. In essence, specific is the mass to raise it by 1 degree Kelvin. What I'd like you to understand is that specific heat has units of joules per kilogram, and a joule is a watt second. So whenever we talk energy, we are actually talking a time element. People think in terms of energy purely as temperature, but in essence, you must understand that energy has a time element, and that is the secret to welding aluminium. So aluminium has doubled the specific heat capacity of steel, and that has a time element. So in essence, what that means is when you put energy into aluminium to heat it up, nothing happens for a period of time, because what you're doing is raising its specific heat, and then it sails away. So with aluminium, what we have is a time element, because energy has a time element in it. When you talk fusion, so we've raised the temperature solid. When you come to fusion, you've got latent heat. Latent heat changes solid to liquid, and aluminium again has a third higher latent heat. So again, what you need to do is put more energy in, but you put energy in terms of time. You pause to put the energy in rather than turning up the temperature. So many people, when they're welding aluminium, think nothing's happening, and the normal thing is to turn the welding temperatures up, and then you just end up with a melt, a disaster. So the other thing that happens is that aluminium has very, very high thermal conductivity. It's about 200% the thermal conductivity of steel. That means that you've got a high rate of heat extraction from weld zones. Bearing in mind that when you're heating aluminium up, you've got a time element, so you're heating time up, but conduction has a time element, so you're actually taking a lot of heat out as you're putting heat in. So always with aluminium, what you see is a time delay. The high thermal conductivity and the high specific heat in essence means that when you're doing welding, what you do is you produce a very large filler bead and a small amount of metal, parent metal, in opposition to steel, where you produce a small weld bead and a big fused base. So aluminium behaves oppositely to steel. In essence, when we talk about energy, the problems we have with aluminium, which are not really apparent with steel, is yes, we've got specific heat, yes, we've got latent heat, but you've got latent heat of the filler and of the parent metal, but you've got significant conduction away. So you need to consider superheat when you're talking about the total energy for welding aluminium. There's that superheat element to overcome conduction. Pause a minute and let's look at electricity. Aluminium's actually quite a good electrical conductor, and its resistivity is about a third that of steel, roughly 1.5 times that of copper. So poorer conductor than copper, you know, a really good conductor compared to steel. So in terms of welding, we consider it to be a very good electrical conductor. We need to drop another thing in. We should talk about alumina in a moment, but aluminium forms an oxide. That is an electrical insulator with very, very high resistivity. So picking up on what we spoke so far, in essence, aluminium has a low melting point, typically about 40% that of steel. Welding temperatures are much, much lower than steel, never more than about 60% of that steel. If you allow for the specific heat, the latent heat, typically you've got to put 300% more energy in than you would over steel. Remembering that energy has a time element. And because of that time element, in essence, your process times are about 30% greater than that of steel. So more energy, greater times, very weldable. Okay. One thing that you need to do when you're welding aluminium, go and buy yourselves a cheap imaging camera. We are invariably welding below red heat. You cannot see what's going on. A very cheap imaging camera will show you what's going on. It will also indicate temperatures. So it's very, very useful to get yourselves one of those. It's part of the secret to good welding. Let's look at another property. Aluminium actually has, when you melt aluminium, it has high fluidity, and particularly the 4000 series, which are based on silicon, have incredible fluidity. And if you talk at the high silicon aluminiums, you can have fluidity which matches that of water. Incredible property for castings. You need to understand that when you're welding, because you're going to end up with fluidity that of water. The 4000 series of aluminium are based on silicon. So silicon is the principal alloying element. And the reason they were developed is you've got parent metal alloys, high thermal conductivity, low melting point. If you try and weld them, you just end up with a pool of liquid. By developing the 4000 series, low melting points down to the low 500s and some of them down to the high 400s. Now you can melt your filler metal with good fluidity without melting your parent metal. So it's an important property. Let's talk about aluminium oxide. Aluminium oxide is incredible because it imparts to it the corrosion resistance that sets aluminium aside from so many other metals. But it's alumina, aluminium oxide. So it's a ceramic. That means it's an electrical insulator. And at 15 microns, the breakdown voltage is about 500 to 600 volts. Very high melting point, about 2000 degrees C. Very high hardness, typically about 900 Vickers. It's also very brittle. One of the things you need to realize is that alumina is much heavier than aluminium. So if you've got alumina forming in a weld pool, it will sink to the bottom as an inclusion. Now, aluminium really develops an oxide instantaneously. If you scratch aluminium, by the time you've walked away, that scratch will start to self-heal. And typically within, if you've got a chemically active surface of aluminium, within about 20 days, it will have developed 10 to 15 microns of aluminium oxide. And that aluminium oxide carries on growing out. It's one of the plateau curves, but aluminium will always form an oxide. It is self-healing and it will grow with time. Important property from corrosion resistance, but you need to understand that it's an electrical insulator, very high melting point. You're going to come across anodized coatings. And in essence, in anodized coatings, we electrically deliberately oxidize the surface of aluminium to produce an alumina coating on it. If you've got an anodized coating, you will never, ever be able to weld it. It's an absolute total barrier. So, alumina, thermal electrical insulator, total barrier. When you weld, you go back to very basic theory. What you do is produce a metal to metal atomic bond, and you've got a ceramic oxide. So you need to remove it. You need to either push it out, exude it, or melt it out. If you're going to do very simple welding, very quick, you can physically remove the aluminium, abrade it away, grind it, machine it. But remember, you've got a short time interval. So if you grind aluminium, potentially you've got, depending on your humidity and the temperature, 2 to 3 hours before that oxide starts to form. You can atomically remove it. You can use electricity, electron flow, by adding a couple of electrons to reduce the oxide and lift it off. You can chemically remove it and passivate the surface. You can upset the alumina out as part of the welding process, a forge weld, and you can melt and shield it with laser welding, with very high temperature methods. You can melt that alumina and remove it. Remember that it's going to have it's heavier weight than aluminium, so it'll sink if you're not doing it. And you can disperse alumina through processes like ultrasonics. So I'm going to pick up on the first one. There's a lot of work going on in the automotive industry in the UK and particularly in the USA, and Ford are now starting to ultrasonically weld aluminium. In essence, ultrasonic welding is a micro explosive weld. What happens is the welding tip is vibrating at ultrasonic frequencies. Because it's welding at ultrasonic frequencies and alumina is brittle, ultrasonic frequencies actually shatter and disperse alumina. And then pure aluminium to aluminium is a shearing thing, so you actually form surface and bulk heating, and it becomes a pressure weld. So ultrasonic welding deals with alumina. In essence, it's a micro explosive weld. Lots of work going on, and Ford has now started to commercialize the process. If you're talking microelectronics and small components, ultrasonics is catching on into the UK as an alternative to soldering. Just pick out a property of aluminium. Aluminium is non-sparking, because when a metal sparks, what happens in essence is the pure metal is burning in oxygen to produce an oxide. Because aluminium will instantly oxidize, very rarely do you see sparking of aluminium, because it forms an oxide instantaneously. So let's talk about a big process of welding aluminium, so fusion welds. If we talk MIG, the beauty of aluminium is you would be DC positive welding. So you connect the positive pole to the power supply. That means that the negative electrons are coming out of the workpiece towards the electrode. In essence, because they're coming up behind the oxide layer, they are actually breaking up the oxide and lifting it up. In essence, there's a chemical reaction coming in. Electricity is the flow of electrons. A couple of electrons are bonding with oxygen to produce an oxygen molecule, lifting the oxygen off. So MIG, when you're using DC positive, because you want to melt your filler rod, self-cleans. If you're doing automated MIG in the UK, a lot of the people are still removing the oxide to speed up the process. With TIG, now you have a problem. The problem with TIG is that if you're going to connect, or ideally you want to connect to the negative pole to keep the electrode cold, but that means that what you've got is an electrical insulator. So if you're going to negative weld TIG and people do for speed, you have to either chemically remove it or grind it away, or alternatively plus pole weld it. And British Oxygen in the UK have developed a technique called plus pole welding, which they are plus pole welding aluminium at very high speeds. Most TIG, for the reason is for the problem of heating the electrode and breaking off the oxide, most TIG in the UK is AC welded or square wave welded. So in essence, in the positive cycle, you're breaking off the oxide. In the negative, you're welding and keeping the electrode cool. We've spoken about aluminium oxide. If you're going to be welding straight after removal or within a reasonable period, you can mechanically brush the oxide off, alumina off, with stainless steels. Just remember to keep your brushes segregated for aluminium. You can Scotch Brite aluminium, you can Scotch Brite abrade the alumina off. Never use emery or sandpapers because they are alumina, and certainly never use carborundum or carborundum grinding stones because they are alumina. In essence, you'd just be putting the coating back. Whenever you abrade, degrease off. The preferred method, and in the UK, is to chemically remove the alumina, and certainly the big automotive companies are either buying pre-treated sheet. So if you're talking body in white, they will buy pre-sheeted sheet, which has been chemically etched away and then passivated and or lubricated. So you might be buying pre-lubricated sheet. The preferred process would be an alkaline etch, then an acid etch, and then a passivate. And the passivate can be hexavalent chromate or a xylate. Both of those are quite acceptable. What you need to be aware is that your final rinse has to be deionized water. And if your final rinse is not deionized water, in essence, what will happen is as you've passivated the surface, you've got a chemically active surface. What you're going to do is deposit all the ions, all the trace elements back onto the surface and liberally coat the aluminium. In service, when they get wet, you're going to get corrosion. So whatever happens, your final rinse must be deionized water when you're chemically pre-treating. We're moving on at a pace, so let's do a little bit of metallurgy. In essence, when we're talking parent metal and filler metals, invariably the two will have different melting temperatures. And as you weld, what you'll form will be a spectrum from pure filler somewhere in the middle to coming out to the outside, an alloy range, and the temperature will change. But one thing that happens is whenever you have an alloy and you melt an alloy, the resultant solidification temperature will be much lower than both of the starting alloys, and it will be a constant temperature. So you can see here we've got A and B welding coming in from there, and what will eventually happen is we will have formed somewhere in the area a eutectic temperature. That eutectic temperature will be significantly lower than either the filler or the parent alloy. In some cases, as much by 150 degrees C. So in essence, what you're going to do, particularly in fusion welding, MIG welding, what you'll have will be a complete spectrum of analyses with a filler, pure filler in the middle, and somewhere between the filler and the parent, you'll form a eutectic, a series of alloys. Apologies. One of the problems you have with aluminium is the big temperature gap from the solidus temperature for when the alloy mix starts to solidify to the eutectic temperature. And if you drop down to 7075, and the 7000 series are regarded as very difficult to weld, pure alloy would melt at 630 degrees, but the eutectic is 470 degrees. That means that you've got a very large freezing zone, and that freezing zone will be subjected to various expansion contraction forces which will pull it apart. So if you have a very large freezing zone, the alloy becomes very, very difficult to weld. High heat of fusion means that when we're solidifying from welding temperatures, it takes a lot longer to cool. So again, you now need to allow time for aluminium to cool. That means that your clamping times are extended, and you need to worry about contraction cooling in the heat affected zone. In fusion welds, there are effectively three types of shrinkage. So you got liquid metal cooling, then you got the solidification cooling, and solid cooling. Now, aluminium has very high thermal expansion, so consequently very high thermal contraction, very roughly double that of steel. We're fortunate in aluminium, it's almost a linear relationship with temperature. With steel, it tends to sail away, but with aluminium, although we have high thermal expansion, it's almost a straight line relationship. And unusually with aluminium, some alloying elements, particularly the silicon elements, which we put into 4000, actually reduce expansion. So with 4000 series aluminium, what you could end up with is a weld that is, as it heats up, is actually contracting, whereas the parent metal will be expanding. So you have contraction and thermal expansion issues. Very, very roughly, if you work on the basis of a 6.5% shrinkage from liquid to solid, that gives you an idea of what's going on in an aluminium fusion weld. What will happen is that manifests itself as hot tearing or hot cracking within the areas of weldments, particularly with alloys that have very large solidification zones. A bit of simplification. Aluminium alloys will form slags, particularly the magnesium ones, the 5000 series, the 2000 series will form copper slags. By and large, these sink to the bottom, and the way to prevent that is by planning to have rapid melting and limit the time that you're at liquid temperatures. So you need to plan how you're going to weld and have a strategy for minimizing liquid metal exposure to the atmosphere. Now, hydrogen is actually a problem of aluminium, but unlike steel, aluminium is not prone to hydrogen embrittlement. So that's one of the properties of aluminium. It's not prone to hydrogen embrittlement. If you're welding, you now need shielding gases, and those shielding gases have to have incredibly low moisture levels, typically a dew point of less than minus 50 degrees C, and certainly a water content of less than 39 ppm. So you're looking at very dry shielding gases. Hydrogen is also produced during the welding process, particularly through electrical reactions, because when you've got damp atmospheres or high humidity and it's condensing on your weld area, when you pass the electric current through, what you'll have is electrolysis and produce hydrogen. Problems with damp filler wire. Now, hydrogen in aluminium is incredibly soluble. So in liquid aluminium has got very, very high solubility. And one of the problems that you have with TIG welding is the high TIG welding temperatures. At the tip of the TIG electrode, you're at temperatures of 1800 degrees C. The solubility of aluminium is incredible. But at room temperature, aluminium has virtually no solubility in aluminium. So when you TIG welding, the position of your weld is important. If you're welding upside down, hydrogen being a low weight gas will actually float up and you'll increase porosity. So when you're designing your welds, be aware of hydrogen and be aware of the porosity. One of the problems that happens on hydrogen is if you've got damp atmospheres or high humidity, hydrogen will actually decompose through a chemical reaction on the surface of aluminium and will form bubbles on the surface of aluminium. Moving on a bit more. One of the most important properties of aluminium is at relatively low temperature, its yield and tensile strengths dramatically reduce and it becomes super plastic. Most aluminium alloys at about 100 degrees C will have lost about 10% of their yield and tensile strength. By the time you're at 400, 500 degrees C, bear in mind it's got low melting point, 500 degrees C, you might be down as low as 10% or 15% of the yield and tensile strength. It becomes super plastic, and the forces to deform aluminium become very, very low. But Young's modulus falls off equivalently. So you see a big drop off with Young's modulus. So you see a loss of strength, but Young's modulus falls off. So now aluminium at high temperatures has a totally different strain rate to that of room temperature. So you now need to understand that you're dealing with a soft or a weak metal with high Young's modulus, which is beginning very differently to room temperature. That has implications when you've got large thermal welds, because the outside of the weld can cool to room temperature, but in the middle, you're still at high temperatures with a low Young's modulus, low strength, you can pull them apart. For the same reason, you can get thermal cracking in the heat affected zones, because the heat affected zones can be at the low temperatures where the parent metal is hot and is contracting, and you can pull it apart. One phenomenon with the 7000 alloys is we can get liquation cracking. If you've held it at a temperature too long, what you'll get is sub-alloys forming with low melting points, and you'll get liquation cracking. And the last problem that you must never forget about is you can get thermal buckling of aluminium. So when you're dealing with thin sheet, you've got high expansion rates, but low mechanical strength. Potentially, if you're not careful, you'll get thermal buckling of aluminium. We're moving on to the pace, but I know you are very, very keen to learn. So let's talk about electrical conductivity. And let me start off with a little bit of theory. The heating of an aluminium of a current is amp squared times resistance. First problem you have is aluminium has low resistivity, so amp squared times resistance gives you a low heating rate. You require a much higher current, about 4 times that of steel, to heat aluminium to the same temperature, but you've got high thermal conductivity, so heat's going to be extracted. And never forget that aluminium's got a low melting point. Implications of spot welding. In essence, if you're going to spot weld aluminium, you need about 300% more welding current and about a 30% increase in process times. Typically, that means you can't use steel spot welding equipment for aluminium because of the higher currents. You've also got a heat sink effect. You've got a tiny weld with big thermal conduction. So current is very important, and you've got high thermal expansion surrounding your weld bead. Big problem that we have with heating aluminium is the resistivity of steel significantly increases with its temperature. So the heating rate Amp squared times resistivity of steel increases, but aluminium has only a small increase in resistivity. So you don't see the resistivity increase with aluminium that you see with steel. So the heating effect is much lower when you're electrically heating aluminium. That means that you have problems growing the nugget. Back to our favorite alumina. If you haven't, a lot of people are spot welding aluminium without removing the alumina. They're requiring on the mechanical force of the spot weld to break up the alumina and form the heating zone. You get a benefit of that because of the high resistivity of aluminium, amp squared times resistivity. The problem is, as soon as you break through that film, your resistivity crashes down and you lose the heating effect. A spot weld and mechanical and forge welds depend on upset. You use the heating to melt the aluminium, but then you have to upset it to get, in essence, the forge weld formed. Problem with aluminium is you've got very low strength. It goes very plastic very easily, very low melting points. So if you exceed them, you have problems. So the problem with aluminium is you need solid, strong aluminium to upset. And you come across the first problem is that the eutectic temperatures of particularly some alloys are extremely low. So you can actually get some melting during the preheat. You're not in the position to upset, but you can experience some melting in the preheat. When you're spot welding, one of the problems you've got is high thermal conductivity, low melting point, a very narrow band of usable plastic deformation, which means that you've got to have incredible energy control and energy input in a short period of time with accurate temperature control. Very tight, narrower controls than steel. Again, we've got high thermal conductivity, very narrow, soft thermal plastic band, high thermal expansion, big volumetric changes. So there's a propensity in aluminium, or there's a high risk when you spot welding that what you're going to do is squirt out your metal rather than solidify it. So with spot welding, you actually need fast heat up and then maintain the constant pressure to form your welds. And again, the problem with aluminium is its high specific heat. So when you're cooling aluminium, you've got to hold it for longer to allow it to cool. So your clamping times need to be extended. And when you're welding some of them, be aware of the contraction in the heat affected zone. Now, aluminium has got very similar thermal conductivity to copper. And that means that we've got up to its melting point, the two have got almost a straight conduction line. Once aluminium melts, the resistivity increases, but that of copper carries on a straight line. So if we're not careful and we're allowing the welding current to run away, what happens is we'll end up with excessive welding currents. The aluminium will melt and it will solder the copper electrode. And what will happen is we'll form a low melting point copper aluminium alloy on the welding, on the face of your spot weld. That now means that you've lost your heat, the electrical heating increase, the electrical resistance increases, it'll now melt at a faster rate. So you have a problem with aluminium buildup on the face of copper electrodes. And typically, if you do nothing, you're going to get about 500 to 700 welds before you formed an alloy and you effectively got a splodgy electrode. So what you can do is regularly buff every 100 or so spot welds, just lightly grind the surface of the aluminium, of the electrode. There's another technique coming out which is called delta spot, developed by Fronius, and what they have is a very, very thin sheet of pure iron, and they pull it between the copper electrode and the aluminium to stop aluminium copper bonding, so they're welding through steel. Just looking outside the box for a few minutes, there's a lot of work going on solid state welding and cold welding, and the Welding Institute is world champion in friction stir welding, invented, champion, developed. In essence, with friction spot welding, a tool is spinning round, it's plastically moving the metal, you've got very localized heat conduction, very localized heat production, which is great because it means that you're overcoming the high conduction rate of aluminium. And the beauty of aluminium in terms of friction stir welding is at low temperatures, Young's modulus drops off, it becomes more and more plastic, mechanical strength forms off. So aluminium is actually perfect for friction stir welding. We've not mentioned this, but aluminium has a very high work hardening rate. So in terms of work hardening, its N coefficient is very, very high. And a high N value means that it work hardens extremely easily, very well, and it also has high drawability. That becomes important when we talk about explosive welding. So explosive welding, we mentioned in very early on about ultrasonics, micro explosive welding, but in explosive welding, what you do is move metals at supersonic speeds and form mechanical joints. The beauty of aluminium is it's got a high work hardening rate and it's got high drawability. So in an explosive weld situation, it'll work harden, but it'll also move at good speeds. Aluminium's non-magnetic. It's actually paramagnetic, which is important because it means that we can use aluminium for electromagnetic pulse welding. And in electromagnetic pulse welding, what you have is a bank of capacitors that you charge up with very high current levels, and then you discharge instantaneously through a coil. And the coil, the discharge through the coil imparts an opposing current in your workpiece, very high electric eddy current flows, and in essence, with electromagnetic pulse welding, what you have is an opposing current which is moving at supersonic speeds. Aluminium becomes viscostatic and it produces an explosive weld. Lots of work going on in researching this at the moment in the UK. I've finished, so I hope everyone's enjoyed that. I'm going to close my presentation off.
That was a very crisp presentation, and you really covered it elementarily. So you covered all elements that happen to play a role in the aluminium welding, and it's very, very insightful. There are a couple of questions if you would like to dig into them. To begin with, there are a lot of MIG welding questions related to that. I would request you to pick up Dr. Krishnan. Are you there?
Yeah, Nimesh.
Could you start with the question so that we can make the most of this session?
Yeah, Mr. Jan, could you locate the Q&A section?
Yes.
Yeah. So there are a few questions here. First one is a very generic thing, but very specific to welding of 6061 T6 material of 10 mm thick, and it looks like there are a lot of problems of porosity in the radiography.
He's not saying what welding method he's using.
MIG.
MIG.
You want me to, he's online, we can get him to have an interactive session with you.
Okay. Normally, the causes of porosity of aluminium are you haven't got your shielding gas right. That's most important. And you've got excessive temperature and also weld orientation, as I said earlier on. To be honest, porosity is not an issue with 6061. It's extensively used for extrusions. 10 millimeters, it shouldn't be a problem.
Yeah, Nimesh, you want to take Prem online so that he can ask precisely what is required.
Yes,
I've got Prem online. Prem, can you, Prem, you can ask your, you can share the details of the particular case.
Yes, good afternoon. Good evening. Hello.
Hello.
Yeah, Prem, we can hear
Hello.
you.
Yes, actually, we are welding 6061 T6 with 4043 and 5356 also. And we are facing problems. We are welding with TIG also. We are welding with MIG also. So we are facing problems of porosities and low tensile strength actually. The requirement of UTS is 235 megapascals. So we are not able to achieve that strength with 4043 and 5356 also.
How are you pre-treating? Let's start off with fundamentals. How are you pre-treating?
We pre-heat around 100 to 150. Pre-cleaning also.
Prem, he's asking if you are treating the metal before welding. So are you using grinding, buffing? Are you cleaning the oxide layers is what Jan is asking. Are you treating your aluminium before you are welding?
Yes, we do some acid cleaning also. And with acetone also we clean. And with stainless steel wire brush also we are cleaning.
Okay, and you're thoroughly drying? Because you need very, very dry aluminium. I mean, 39 ppm water is a dew point of about minus 50 degrees C.
Yes. Yes, we are welding in a dust-free enclosure and a humidity control room also. Humidity is less than 55%.
Okay. You should be able to weld it. It should not be a problem. I need more details. I'm looking at your filler choice. In essence, if you're using 4043, you will have trouble in meeting the mechanical strength of the UTS. First of all, T6 is quite a high temper, and 235, you will certainly, if you're using 4043, you will certainly be changing the analysis and you will struggle. Well, you're not going to achieve the mechanical properties of that. The problem, because you've changed the chemistry, I would look at changing your filler metal.
Which one would you recommend?
If you drop me an email, I'll get you some details on alternative filler metals. But you certainly won't. If you use 5356 or 4043, neither of those are heat treatable alloys. Certainly, the 4043 will certainly dilute down the 60. You will lose all of the heat treatable properties. You need to neither of those. If you're looking to develop that, you need to change your filler metals.
Okay, so Prem, what we do is you already have Jan's email ID. We will share it again with you. I request you to email him directly and take it further so that he can suggest a proper. Looks like the choice of filler metal is where you are having a problem, and he may help you with that, right?
Yes, most certainly.
Yeah,
Thanks a lot, Prem. I'm going to put you on mute again.
Yes, thank you.
Yeah, now we have another question in the forged weld. It's regarding the grain flow pattern will change after heat treatment. The question is,
no, the grain flow is inherent through the forge. It will not change. And that's why important in a forge weld, realistically, as you upset, you really want to maintain the grain flow at about 45 degrees at the weld center line. So at the outside edges of your forge weld, you really want about a 45-degree grain flow. If you go much higher than that, if you go to sort of 70, 80 degrees, you'll start losing mechanical strength because the weld will try and tear away. Much less than 45 degrees, you're not getting the right amount of upset in it. But the grain flow won't change in a forge weld with heat treatment.
Okay, thank you, Jan. Another one is on, again, on porosity, how to eliminate porosity in MIG welding. And also why shielded metal arc welding is not used. I guess it is with respect to aluminium.
You don't need it in steel because you're not going to form an oxide. The problem with aluminium is that you will form oxide. We will happy to send you a PDF of this presentation.
Yeah, fine. So that we can circulate to all the participants.
Most happy to give you a PDF of this presentation.
Yeah, sure. So in aluminium welding, from what thickness we have to do preheating? And what is the best recommended process or equipment to preheat aluminium? And what is the recommended temperature for preheating? It's all about preheat.
Very, very roughly about 150 degrees C in maximum preheat. You don't need a lot of preheat of aluminium. In the UK, very few people are preheating. They're normally just welding aluminium cold. About 150 degrees C, just a dry oven would be perfect for aluminium. You don't have high temperatures. It's the filler wires that you need to preheat. And realistically, you need to preheat them for about 150 degrees C for about 24 hours if you're MIG welding. So it's not the aluminium, it's the preheat, it's the filler wires.
Okay, thank you. And there is one generic question: why TIG DCN is not recommended, and why we go for AC in aluminium welding?
The problem with plus pole welding is that you'll melt your tungsten electrode. And that's why British BOC, British Oxygen in the UK, Lindy have developed plus pole welding. You would like to plus pole weld TIG. The problem is that what happens is the electrode overheats very rapidly and you'll actually melt the electrode. That's the pure reason. That's why people use AC. And the move in the UK is to use square wave AC. So you get maximum heating and minimal melting.
Yeah, okay. And in continuation, there is one more question. Which type of electrode do you recommend? I mean, the tungsten, it's a thoria based or a cerium based?
Either, but there, in the UK, at the moment, there are scares about the radioactivity of thorium. So there's no problem. Either of those, it really depends on your welding temperatures and the process. Both of them are used. You need to change the tip. But as I say, the problem with thoria in the UK is there are some scares about radioactivity at the moment.
Okay, and another one is one of the practical problems seems to be regarding some welder qualification on aluminium 6061. There is a problem with porosity. So they have tried all so they have tried all cleaning methods and tried the different shielding gases like argon, helium, 8020, still facing same problem.
If they drop me an email, I'll send some stuff through. And
I think both the questions are the same. So maybe we can pass it over to both of them.
Yeah. Jan, I would request if you don't mind, share the presentation for this particular activity with us as well. So we'll upload it in the Knowledge Center part. So people.
I'll email the email to you, the presentation to you. It'll probably be on Monday morning. You're welcome to share it.
Okay. No worries. Thanks a lot.
So now another one is on why weld strength is more than has with non-heat treatable, where weld strength is lesser than HZ. Another one.
Read that.
I think the question is not so clear.
I don't understand that. Why is weld strength more than heat affected zone in heat effect? It can't be. It can't be. Your stress relief, your heat affected zone. What happens in non-heat treatable alloys? So work hardened, strain hardened. I'm assuming it's in the strain hardened, work hardened condition. What will happen is that you will stress relieve the heat affected zone. The problem with aged alloys or heat treated alloys, it really is a function of time and temperature, because with a heat treated alloy, in essence, you're looking at an aging process. Your fusion zone will have taken it into solution. Depending on the alloy that happened and depending on how big your heat affected zone is, you can overage it, and you can overage the heat treated zone, but you shouldn't see the heat affected zone in either heat treatable or non-heat treatable should certainly lose strength. So again, I need that. Okay.
Yeah, so there is one more query on 6 series T6. What are the precautions to be taken for GMW? And again, which filler wire is advisable? So I think this is a very generic question by most
I
of
will
the
send you,
yeah.
if you drop me the questions in an email that I need to answer, I will get the answers back to you on Monday.
So Mr. Jan, what we can do is we will compile all these questions. Yeah. And we will also ask the participants if at all they have something that they can send us over mail.
Yes. And then I'll get them answered to you on Monday. It'll be, you'll get.
So, yeah, so all can be compiled and we will send it to you.
These particular questions that are there, that I will download immediately after the talk, and I will share it via email to you today itself. And anything that comes in later, I will share with you again.
Okay, right. Someone's asking about a good welding book reference. I haven't found one.
Maybe you should write one.
You should write one.
I haven't found one. I'm sorry, I haven't found one. Someone's asking is to weld stainless steel to aluminium, stir welding.
Stir welding.
Stir welding. And the TWI in the UK are the world leaders in that.
It's also possible to do a little bit of brazing on that, yeah? Yes. Aluminium brazing?
Aluminium brazing's done. There's a lot of research going on in the UK. The secret of aluminium brazing is the fluxes.
Yep. So that is also possible.
Yep.
Yeah, again, I think something on the 5000 series, is it more prone to porosity? If so, why, and what special precautions needed?
I think we've covered those. We'll be right. Can we use vacuum laser welding to weld aluminium? As long as you've removed the answer is yes, but remember, aluminium's got a very low melting point. Vaporization temperature of aluminium is 2,400 degrees C. If you hit aluminium with a laser beam in a vacuum, you're going to have a lot of aluminium vapor in your vacuum. You're going to end up coating everything with aluminium. Nice. Theoretically, you can, but the melting point, the vapor point is only 2,400 degrees C. Your lasers at about 4,000. You're going to end up coating everything with aluminium.
Yeah.
The visual gases you'll see within pure gas will be unstable arc straight off, but porosity. It's as easy as that.
Okay. And
I'm at my depth with welding aluminium and magnesium. Chris will have to take that one away.
Yeah, I think we will give it to Chris later.
Right. Okay, there's an interesting one on this thin sheet welding. There's a process called cold metal transfer, CMT. I think you might know it as MIG, micro MIG. I haven't covered it, but if you're welding thin sheet aluminium, the way to do that is cold metal transfer, CMT, or micro MIG. If you want to Google a company called Feronius and CMT, they're probably the world experts on thin sheet welding.
Yeah.
They have a good presence here in India as well.
Yeah, 7075 by resistance, very, very difficult. That's why aircraft are spot weld. That's why aircraft are riveted. I would say no. I don't think you're going to successfully do 7075.
Okay. Again, aluminium laser welding.
If you're fiber welding aluminium, no issues. With LED lasers and with fiber lasers, the reflectivity problems have been got over with. The problem with laser welding aluminium is it forms a plasma field which is unstable. And the developments that I've seen, particularly with a company called IPG Photonics, they are using a laser beam. They're using fiber lasers. They split the beam into 3, and they are running 2 laser beams ahead of the main beam through fiber optics. And the 2 beams create a plasma field, which is stable for the main welding thing. So if you want to aluminium laser weld aluminium, have a look at a company called IPG Photonics. Again, if you ask me the questions, I'll send you the details.
Okay.
Another one.
That one's too technical. I've got to take that one away. Okay. Bead profile. You're not putting enough energy in. It's as simple as that. You got a nice bead because you're not putting enough energy in.
You got to change your balance. The AC wave balance needs to be changed so that you can have enough penetration, and the bead profile also remains the same.
I think there are 2 more questions on friction stir welding. I think we will take help of Chris later.
I mean, the Welding Institute is the expert on that.
Yeah.
Yeah, Jan and I will look at some of these together, and between us, we'll get you a good answer.
Yeah.
Right. There's an interesting one about using activated TIG welding process for the 6 series. Is it possible to use activated TIG?
I think Chris, Mr. Vinod Kumar is working something on that. Maybe we will check with him. Yeah.
Okay. 5083, you have a problem with the 5000 series. Once you're over 3% magnesium, they are prone to stress, corrosion, cracking fundamentally. You can't overcome it. That's a problem with 5083. Once you're over 65 degrees C, you will form beta phase and it starts stress, corrosion, cracking. Fundamental problem with the 5000 series alloys. We've got a filler chart, which I will email over to you guys when you ask.
That will be really useful for all of us.
Okay.
So I think we are almost
To be
done.
honest, if I was welding low thickness to high thickness, I'd look at spot welding. That would be the one.
This is Mr. Binoy Nair.
Yeah.
It would be spot welding.
Yeah. I think we the very last one is the ideal. It's horses for courses. It's not a fair question.
It depends on what material, what thickness, what grade.
Exactly.
A lot of questions. So yeah, I think throughout your presentation, you covered it fairly well, where it says what are the difficulties which happen because of the different compositions. And that was a really, really insight in a very, very simple way. You demystified aluminium welding for us. So Chris and Dr. Krishnan, Would you now, I think Ashok is back. Ashok,
Yeah,
Mr. Ashok Malge.
I am back.
Yeah, before we
Oh,
get
we
into
get
the
to Mr. Malge.
yeah,
Chris,
before we
Sorry.
get into the vote of thanks,
Yeah.
Dr. Prakash, can you say hi to all of us?
Oh,
Hello.
Yeah, maybe you
Yes,
can on
Dr.
your
Prakash.
video and
Yeah,
speak
yeah,
for,
I'm starting. Yeah.
yeah, speak for a couple of minutes.
1 second. Is it visible? Hello.
Yeah, please go ahead.
Yeah.
Okay. Okay. Hi, hi all, and my special thanks to Indian Institute of Welding as well as Jan, first of all, because when I spoke with him 2 days back, he told me that there is a good opportunity to interact with Indian Institute of Welding on Saturday. So thanks, Jan, for introducing me to this panel, and also for the wonderful presentation you gave on aluminum welding and challenges. And it's also good opportunity for me to meet Chris at TWI. We can talk later on a lot of welding related stuff we are doing at WMG. So as Krishnan mentioned, I am working as associate professor in WMG from 2014. Before that, I was at Manchester and did my PhD in Canada. So some of the questions are very interesting. I can see, especially about the porosity issues. That is where my whole expertise of welding related stuff is going. Even we are studying like in casting as well, like aluminum casting porosity is a big problem. If you can see, like some questions asked about whether we can do vacuum and prevent porosity. Just to give some academic type of study we are doing, not just for industrial purpose. So there are two types of porosity. Whatever I am understanding from the questions is basically about the gas porosity. I think that is where people are thinking how to put vacuum or how to use different shield gases so that you prevent the hydrogen solubility. But there is another main important porosity which we need to consider is shrinkage. So what I see is basically there may be big chunks of pores with not exactly spherical in shape. They may be from the shrinkage porosity, which is related to the alloy itself and the solidification conditions compared to the solubility of the gases. So, so if you can see in that way also, then you can understand more about the porosity formation. That's what I can say. Yeah.
Yeah, thank you so much.
and wonderful opportunity to engage, and we also doing lots of dissimilar metal joining, like joining
That will be
steel to
interesting. Yeah.
steel to aluminum, because nowadays, as you see, this concept of multi-materials and hybridization is coming in automotive applications, because you cannot completely eliminate steel. At the same time, you cannot completely make automotive like fully aluminum because of the cost aspect. So the main challenging issue is to use the right material at appropriate locations. So in that way, we thinking like, okay, how to join steel to aluminum. Again, the same issues are coming, like intermetallics formation, defects formation, and as Jan mentioned, a lot of challenges with aluminum as thermal conductivity, coefficient of expansion, melting point. But steel side, you have very, very high melting point, all this. So these are all the big challenging issues. But we are trying to see more academically. But when I see from industry, that is again different challenges, because how to scale it to this to industry level is always a challenging aspect. So in that way, it would be good for me also to interact with the Indian Institute of Welding Society, so that we will learn more about the industrial problems. And also, I'm working with Indian Institute of Technology, Kharagpur. You might have known Center of Excellence of Advanced Study. They recently formed.
Yes.
So so they also have lots of friction stir welding, electron beam welding, laser welding kind of studies going. So that is simply about myself, and any questions I would like to take, or it's nice meeting you all.
Thanks.
Thank you. Yeah, thank you so much, and we will be surely in touch with you.
Sure.
Yeah.
See, I can, before we get into the vote of thanks, I can tell you that India is right now in the middle of a lot of growth. Contrary to the belief, I think there are challenges and opportunities happening. More of opportunities are coming in, and aluminum plays an important role. You look at a lot of development in aerospace, defense, light military vehicles, and auto sector itself is moving into EV, where they want lighter vehicles, therefore moving more towards aluminum and its compositions. Even the batteries, the EV batteries, rather, last week I had a detailed discussion about welding of the aluminum bus bars to the battery formation of EV batteries. Now, all these are various applications. Even Indian railways are moving towards aluminum. So there will be a lot of development happening, and I'm sure we are going to keep, probing Dr. Prakash, Chris, and Jan here time and again when we come across a lot of challenges and try to make the most of it. So thanks a lot for devoting your time on a Saturday morning. And now I hand it over to Dr. Malge, Ashok Malge, to please convey the vote of thanks.
Thank you.
Thank you, Nimesh. Am I audible?
Yeah,
Yes, you are.
Okay. Good evening, Jan, Chris, and
Hi.
Dr. Prakash, and all participants. This is Ashok Malge, Secretary, Indian Institute of Welding, Mumbai branch. It's my privilege to propose vote of thanks on behalf of IIW Mumbai branch. I thank Chris of TWI for introducing very nicely about Jan. I thank Mr. Jan for giving a very elaborate talk on welding of aluminium, covering all technical aspects. And it's aluminium and aluminium alloys are difficult to weld material which is conceived, but he made the talk very interesting, giving all the fundamental and practical aspect of that. The talk was very educative and interesting. All the participants have got benefit out of this. I also thank all the participants and for attending this talk. I also thank our technical team, Dr. Krishnan, Mr. Nimesh, and Abhishek Vyas for making this a successful event. Thanks. Thank you, one and all. Over to Nimesh.
All right. Thanks a lot. And I'll be sharing the email to you shortly with the list of questions so that you can have your weekend cut out for the replies on the Monday. All right. Thanks a lot again. And Chris, we're going to keep coming back to you to get us more and more experts from the UK and around the world so that we can, share the knowledge with everybody here back in India and hopefully make something good out of it. Thanks a lot once again.
Cheers, everyone.
Like thank you for the new part-time job. I'm really enjoying it. Bye. Bye.
Thank you, Chris. Thank you.
Thanks a lot.
Bye.
Thanks.
Thank
Bye-bye.
you so much.
Ciao.